I welcome you to this presentation on reconstructing occluded elevation information in terrain maps with self-supervised learning. I'm Maximilian, and this is a joint work by the Robotic Systems Lab at ETH Zurich and the European Space Agency. Modern mobile robots usually rely on 2.5D digital elevation maps for traversability analysis and motion planning. These elevation maps are generated based on depth sensor data recorded with LiDAR or stereo cameras. To enable safe and optimal path planning, we strive for complete and accurate elevation maps. In practice, however, our robots often encounter occlusions caused by terrain discontinuities such as rocks, obstacles, or convex terrain, which hide an area patch from the sensor's viewpoint. Further, depth measurements can be degraded due to reflections, stereo matching failures, dust, or textureless surfaces, which frequently all lead to additional missing elevation information in the DEM. An incomplete elevation map severely limits the planning horizon, as seen in this example. Oftentimes, the robot has to stop, replan when more of the environment becomes visible, and this really slows the robot down. The naive solution would be to use self-supervised learning to train a neural network to reconstruct the missing elevation information. However, in the real-world datasets, there is rarely ground truth information available, which is required for supervised learning. We aim to bridge this gap by introducing a self-supervised learning strategy, which does not require access to ground truth information. We consider elevation maps generated by all kinds of mobile robots, such as, for example, legged robots or planetary robots. Conventional elevation mapping strategies generate partially occluded DEMs. We randomly sample a vantage point and perform raycasting. This means we check for every grid cell whether it is visible from the vantage point. This leads to an even more occluded DEM with a corresponding binary occlusion mask. We pass both of them through an encoder-decoder neural network to receive a reconstructed DEM. Next, we compute a reconstruction loss between the reconstructed DEM and the input DEM. Finally, using this loss, we backpropagate and update the neural network weights. In our experiments, we first consider multiple synthetic data sets containing both structured and smooth terrain types. We observed 24 to 90% reductions in mean squared error compared to interpolation-based baseline methods for these synthetic data sets. More importantly, self-supervised learning only performs slightly worse than supervised learning on these synthetic data sets. Next, we validate our method on real-world data sets without ground truth information collected with Animal, which is a legged robot, and a planetary robot testbed. We achieve 52 to 82% reductions in mean squared error for these real-world data sets. On top, we perform motion planning with incomplete DEMs. On the bottom, we use our reconstructed elevation maps to do this motion planning. Our preliminary experiments show that the planning enabled by our approach can reach further ahead and only needs to be slightly adjusted when the belief of the occluded area is updated. Thank you for your attention.